look at. And it doesn't make sense to talk about shorter distances than the typical scale at which this happens, which is 10 to the minus 33 meters. And just, I mean, it's always hard to have an idea on powers of 10. So remember, there was the proton. The proton is 10 to the minus 5 meters in diameter. So you take 1 meter, scale it down to the size of a proton, and then you scale it down for another time the same factor, then you reach this. So it's completely, I mean, out of reach for experiments today, at least. But theoretically, it's an important thing to look at. And that's my area of expertise. So the most promising, as far as I'm concerned, and I would say most of my colleagues, the most promising approach is called string theory. And the idea is very simple, and that is actually the particles, the different particles, are not different particles. Well, first of all, if you look inside them and what they really are, they're not point-like. I mean, I've drawn them here like big chunks, but I mean, they have 0 diameter. But they're made of little rubber-type strings, and what this string can do, it can vibrate. So I've drawn here 3 different vibrational modes, and what looks like 3 different particles are actually just 3 different vibrational modes of the one string. And the appealing feature of this very simple idea is, I mean, here I'm just talking about particles, and actually I'm talking about quantum physics. But when you do this, and you come up with this rubber band, and you look at what kind of particles you produce, you see that no matter what you do, you always produce something. Okay, you always produce something that is a graviton, which behaves as the particle that communicates gravity. So string theory, no matter what you do, always has gravity, and it's by construction it's a quantum theory. So string theory is a theory of quantum gravity, and it's the only known powerful, consistent theory of quantum gravity that we have. So the way this works is when there are these diagrams. So time goes up in this diagram. So 2 particles here meet and collide, they form 2 new particles, they come back together again, and they form 2 new particles. That's, I mean, the archetypical particle collision diagram. I mean, you not necessarily have 2, you have many, like you've seen before, but you can also have 2. In the string theory language, it looks like this. So you have one string, you have another string, they come together, here they fly together, then they join, they form just one big string. This disintegrates again into 2, one here, and then they come together, and then disintegrates again into 2 strings. And what you see in this picture, I mean, this is the same picture as this, just from the stringy perspective. And what you see, I mean, the important thing about this is this diagram has special points where stuff happens, namely here and here, right? They're old particles forming new particles. This does not happen here. I mean, here, any point on the surface is just as any other point, especially the point here where I pointed when I said the stuff comes together. You just rotate this thing a little bit, then it's not this point, but maybe it's this one. So this point, when you look at it closer, is just as good as this one or this one. Okay? And that is a conceptual big advantage of string theory, because you don't have to explain how this works. You just have to say string, and it's all built in. You just say how this little bit here works, and then all these interactions are already built in. You have no freedom to decide. Okay, one last thing about is extra dimensions. So I have to say there's one big disadvantage of string theory, and that is string theory wants to live in 9 + 1 space-time dimensions, although we only see 3 + 1. So we have to get rid of 6 dimensions. So it looks like this theory is complete bullshit, right? But it's not, because there's this thing you can do that's called compactification, and that tells you when stuff at big scales look like it has certain dimensionality, it can be wrong at small scales. So for example, there's again our friend the fly sitting on some sheet of something. So this is something 2-dimensional. But actually, the 2-dimensional thing is the surface of some pipe, right? And when you zoom out, when you go to bigger scales, it looks like this. I mean, I've zoomed up the fly, but this is now something 1-dimensional. But the idea is when I go back something one-dimensional can actually be two-dimensional when you zoom in. Right? And the same thing happens in string theory. Okay, here, cat content, but you're supposed to look at the carpet. So this Filcati carpet, when you're far away, looks two-dimensional, but when you zoom in, you see actually there's the wiggly stuff. It's actually three-dimensional, so it's one dimension higher. Okay, so the string, now you do the same thing, just with at each point in space-time, when you look at it closer, there's something six-dimensional. There's this archetypical drawing of something six-dimensional. It's of course not six-dimensional. The drawing is even something two-dimensional. But everybody thinks this is how six-dimensional stuff looks like. So that's the idea of the compactification. And the problem is, I can talk about this, but there's not a unique way to do this compactification. There are roughly 10 to the 500 ways to do this. And unfortunately, our particle physics, the types of particles, I've shown you the types of particles we see. The exact details of these particles are determined by the choice nature made for this six-dimensional space. And since there are many possible choices, even though the string theory by itself is unique, the way the compactification is not. And that means the so-called low-energy physics, so the particle physics that comes out of it, that we see at our scales or at LHC, there are roughly 10 to the 500 possibilities. So it's not very predictive at this scale. But when you zoom in such that you see the 10-dimensional nature of space-time, then it's unique. So this question of whether you can measure string theory or not really hinge on the question whether you think it's, at least in principle, possible to bring up such high energies that you see the 10-dimensional structure. So that's the end, so I had to include a cartoon as well. Yes, science is an open process in which a good idea can come from anybody. Yes, widely believed theories are on occasion overturned by simple thought experiments. And yes, your philosophy degree equips you to ask interesting questions sometimes. But you do not just overturn special relativity, a subject you learned about an hour ago, with your race car on a train idea. You just don't like that I'm turning a rational eye on your dogma. Hey, what's the email for the president of physics? So this is my last slide, which is about open source physics. So what do I mean by this? There's a conflict, right? So everything that we do is open. We publish everything in the open. You can go to www.archive.org and dig up all the order of 20 to 30 papers we write every day about string theory, and you can read it, and you can read about the data that they measure at LHC. You can even download, the data in the cosmology, in these cosmology pictures, you can go to NASA's website and download. It's about 3 megabytes of numbers, and you get the numbers that produce these plots. And you can do your own physics there. So it's open in a sense. Everybody can do it. On the other hand, it roughly took me 10 years to learn this. To a level not that I can present pretty pictures, but I can do calculations. And that's the problem here. So of course you're all welcome to join us. But unfortunately you probably need more than half an hour. But still, it's open to the scrutiny of everybody who's ready to invest a significant amount of time. But you have to invest this time, because I also want to say that, my colleagues and I, we're getting emails from people who came up with their private little theory of why relativity is wrong or why string theory is obviously bullshit. And they got this idea from looking at these pictures. But I have to show you, it's a bit more, there are formulas behind these pictures. And I think it's the most interesting thing in the world you can do, but it needs some investment of time. But this is like in every non-trivial thing. Okay, thank you very much. We have like 1, 2 questions. So, microphones are there. You know this for day 4.
Right, I would ask anyone with a question to line up on the microphone over there, please. Short questions.
Okay, I'll be outside if you don't catch me here.
Great.
Okay, there seems to be one question. Hi. Shoot.